Hello students, welcome back to the second session on process management of Unit 2. In this lecture, we will learn CPU scheduling. Before I begin CPU scheduling, let's review the first session on process management. In the last video, we have seen process definition. It says a program in execution is a process and a process has to execute in a sequential fashion from the first statement to the last statement. So we have already seen in the last lecture that the memory allocated to a process has different sections. The memory is divided into different sections. These sections are text section, data section, heap, and stack. The text section contains the program instruction to be executed. Data section contains the global data of the program. Heap section contains the dynamic memory allocation, and the stack section is used for local variables and function call management. Next is process control block. The process control block is used by operating system to store information regarding process during its life cycle. It stores this information on a PCB. It contains process state, process number, program counter, registers, memory limits, list of open files, and other information. We have already seen this in the last lecture. You can just go and view that last lecture. Next, we also saw the list of queues that are present in the system. This snapshot shows a list of queues that are used by the operating system to manage the process execution. Here we have a ready queue, the first one, which is containing two processes. Next we have the magnetic tape queues, then we have the disk unit queue, then we have the terminal queues. All these queues are maintained because the operating system keeps track of which process is getting executed at what level, where is it present in the system, and where it has to be brought next. So that is what we have learned in the last lecture. In this lecture, we will start with CPU scheduling. So let's understand what is CPU scheduling. CPU scheduling, here a system can be a single processing system or a multi-programming system. A single program system is a single process can be processed till the process terminates. That means the CPU is allocated one process, and wherever it is, whether it is in waiting queue or whether it is in IO devices, the process CPU is not allocated any other process. Till that process terminates, the CPU is going to execute a single program. So once it is admitted, till it terminates, the CPU is not allocated any other program. That is called single program system. Whereas a multi-program system works in this way. So a process P1 is given to CPU. It is executed by the CPU. Maybe it will go to a terminate state or an IO device state. At that time, the next process is given to the CPU. That means the CPU is never idle. It is always allocated some or the other process. So in this way, P2 also gets processed when P1 is either in an IO processing or it has terminated. When process P2 also leaves the CPU, the scheduler dispatcher allocates CPU the next process in the ready queue. So in this way, it goes on allocating new processes to the CPU, and whenever the other processes who have finished part of the processing and have gone to IO devices come back and join the ready queue, and they are again allocated the CPU. This is called multi-programming. So in this way, multi-programming achieves maximum CPU utilization. A process, when it is in execution state, it will have a cycle. Its execution is in terms of cycles. These cycles are either a CPU cycle or an IO cycle. So this is called a CPU burst or an IO burst. So next we'll see what is CPU burst and IO burst. That there are few processes in the ready queue, and there is a short-term scheduler that will select any of these processes and give it to the CPU for execution. This CPU has a dispatcher which takes care of the context switching. What is context switching? We have seen in the last class that when one process leaves the CPU, it has to remove all the information about that process from the system, CPU system, and it has to load the other process details into the CPU for execution. That is called context switch. So this is done by the dispatcher here. So how this is provided to the CPU for execution. So the process P3 is in CPU burst. And now if you also see that process P6 has gone from the waiting queue to the IO device. So it is in its IO burst. Process burst and an IO burst. All the processes go through this process burst and IO burst. Now some processes will have very less IO burst and a lot of CPU burst. That means it has a lot of processing to do and less of IO to be taken. And some processes are basically majorly IO burst processes than CPU burst. It means that these processes work more on IO devices and less in the CPU. So processes have to be a good mix of IO burst and CPU burst so that all your CPUs and IO devices are kept on all the times. For this, we have certain scheduling criteria that will make the scheduling algorithms appropriate for having a good mix of IO burst processes and CPU burst processes mixed so that all your resources are always engaged. So what are these scheduling criteria? The scheduling criteria is first one is CPU utilization, second is throughput, third is turnaround time, fourth is waiting time, fifth is response time. So CPU utilization, what is the CPU utilization? CPU utilization means keep the CPU as busy as possible. So the CPU should always be processing some process in the system. So if there is any process in the ready queue and if the CPU is idle, then the process in the ready queue has to be allocated to the CPU for execution. So that is always keeping the CPU busy is what is CPU utilization. What is throughput is the number of processes that complete their execution per unit time. That means if I consider 10 milliseconds, in 10 milliseconds, how many processes complete their execution is the turnaround time. Or you can say in 1 hour, how many processes finish its execution. So whatever unit time you take, that in that unit time, how many number of systems are getting executed is what is the throughput. So if one system executes 5 programs in 1 hour and another program finishes 10 programs in 1 hour, that means the second system's throughput is higher than the first systems. So more number of processing finishing is what we also expect. Next is turnaround time. A turnaround time is the amount of time to execute a particular process. A process, when it is admitted into the ready queue as a new process, till the process is terminated at the end of its execution, this time that it takes in the entire system, whether it was interrupted in between, whether it is gone to an IO request or whatever waiting it has done wherever in the ready queue, in the waiting queue, wherever it is, it should finish its execution as soon as possible. This amount of time that a system takes to execute a process is called turnaround time. Next is wait time. The waiting time is a time taken by the processes to be waiting in either ready queue or in any of the IO device queues. So amount of time a process has been waiting in the ready queue is what we call as a waiting time. Next is response time. Response time is the amount of time it takes from when a request was submitted till the first response it produces. It is not the output, it is only the response. So this is in terms of time sharing environment. We will see this when we come to time sharing environment. Next is how we can optimize the scheduling algorithms criteria. So what we need is, we need that the CPU utilization should be maximized and the throughput should be maximized. That means the CPU should always be busy and the number of processes finishing its execution from the system should be maximum. Whereas the turnaround time, that means the total execution time should be less, the waiting time of the processes should be less, and the response time also should be less. So if we are able to achieve these criteria with max and min conditions, then that algorithm is called the best algorithm. So let's see now what are the scheduling algorithms. Scheduling algorithms are first come first serve scheduling, which is basically a non-preemptive. What do you mean by non-preemptive and preemptive? I will explain you in a while. Next is shortest job first or shortest remaining job first. So this is a preemptive as well as a non-preemptive scheduling algorithm. Next we have priority scheduling, which is again a non-preemptive and a preemptive scheduling. And we have round robin scheduling, which is non-preemptive. So what is a preemptive and non-preemptive now? If supposing P1 is a process that is allocated to the CPU for execution, and while it is executing, another process P2 comes into the system and this process is having a higher priority, then process P1 will be stopped its execution in between. It will be put back into the ready queue and P2 will be given for execution. So we will see this with examples and with animation how preemptive and non-preemptive works as we go through these algorithms. So the first algorithm here is first come first serve algorithm. This is the scenario where we have the CPU, we have the IO, and we have the CPU scheduler, which is an FCFS algorithm based. So some P4 has entered the system with a CPU burst of 14. So this process will be allocated to the CPU because it's the only process in the system. Next, P2 comes into picture and this process is having a CPU burst of 5. CPU burst of 5 means it has 5 milliseconds of task to be completed in the CPU. Next we have P9, which is having a CPU burst of 20 milliseconds. So right now one process is already in execution. So CPU is executing that process. Then this process, if it's finished its execution, then it will exit and hence the next process will be given to CPU for processing. So while this process is getting processed, it may require an IO. So it will go to an IO processing and that time its CPU processed, the next process will be given to the CPU for execution. So when this way, the first process that entered the system gets the CPU. So immaterial of whether the process is a smaller one or the process CPU burst is of a higher one is not considered here. The process, how it have arrived in the system, that order only they are allocated to the CPU for execution. So next is shortest job first algorithm. In the shortest job first algorithm, as the name suggests, it says that whichever process is having a smaller CPU burst will be allocated to the CPU first for execution, and the processes which are having higher, so that means in ascending order of their CPU burst, they will be allocated to the CPU. So let's see that. So here P4 is a process with 14 CPU burst. So it is the single process. So that's obviously the smallest CPU burst. So it is running. It is given to the CPU and it is getting processed in the CPU. Now another process comes into picture, that is P9, which is having a CPU burst of 5, and P2, which is having a CPU burst of 20. But the CPU is already allocated a process P4 with CPU burst of 14. So until unless it doesn't leave the CPU, the other two processes have to wait. So when this process P4 comes out of CPU, it is that time the next process is allocated to the CPU. So in this case, what do you think? Which process will be allocated to the CPU, P2 or P9? Now, if you see, P9 is having a CPU burst of 5 and P2 is having a CPU burst of 20. And this algorithm works on shortest job first. So here the shortest job is a job with a CPU burst of 5. So hence the P9 will be given for execution. So P9 will go for execution and P2 has to wait in the system because P2 is having a CPU burst of 20. Now if you see, P4 finished its IO processing and has come back into the system with a burst remaining as 8. CPU burst remaining as 8. So now CPU is executing process P9. So if it finishes, it exits. And when it exits, then again the scheduling algorithm has to select the smallest. So which do you think will get executed next, P2 or P4? P2 is waiting from a long time, but P4 is the smallest CPU burst process. So it will be allocated to the CPU and it will get executed by the CPU. So when this exits or it goes into an IO, that is when P2 is given to the CPU for execution. This is how a shortest job first gets executed. So even though the ready queue was having a smaller CPU burst process waiting, it did not disturb the running process. So this is called non-preemptive algorithm. Next, we will see the shortest job first primitive version. So here you remember that if there is a process running in the CPU with a higher burst process, then it will be removed for a process which is having a lower burst process. Let's see that now. So here again P4 with CPU burst of 14 has entered the system. Since this is the single system in the single process in the system, it will be allocated to the CPU for execution, and as it is getting executed, P2 comes into picture wherein it is having a CPU burst of 20. Now if you remember, P4 is having a CPU burst of 14 and P2 is having 20 and P9 is having a CPU burst of 5. Since P4, which is in the CPU, is getting executed and it's having a CPU burst of 14, it is a higher CPU burst than P9, so it will come back from the CPU. It will be preempted, means removed from the CPU, and the smaller P9 process will be given to the CPU for execution. So smaller job first is what is this algorithm's motto. So it will process that, and then if that gets completed, then the next smallest will be allocated to CPU and it will get executed, and lastly the largest CPU burst process will be allocated. So in the previous slide we saw that the process was not removed, P4 was not removed from the CPU. When it left the CPU, it was then that P9 was allocated to CPU. But here, since it is a primitive version of the algorithm, the running process will be halted in between and the smaller process will be allocated to the CPU for execution. This is called shortest job first. Now what is the drawback of a shortest job first? The drawback of a shortest job first is that this CPU burst calculation cannot be done practically. We cannot tell in advance which process will require lesser time for execution and which process requires more time for execution. Whereas it can be done theoretically. We can calculate the CPU burst by analyzing the previous executions of these processes, but still it's not accurate. It is just a random calculation which cannot be accurate, which we can be close to the actual processing time required, but we cannot be accurate to the actual time taken. So that's why shortest job first is the most efficient algorithm, but the problem is calculating the CPU burst. Next is priority algorithm. The priority algorithm is where the processes are executed based on priority. Now the same process P4 is having a CPU burst of 8, but its priority is 4. So it is a single process, so it is given to the CPU for execution. And next we have a process coming in P1 with a CPU burst of 10 and its priority here in red shows 1. So that means the process, since this is a non-preemptive algorithm, running process will not be disturbed, and hence when it leaves the CPU itself, that is when the other process with a higher CPU with a higher priority is given to the CPU for execution. Next process is coming in to the system is P2 with a priority of 2 and CPU burst as 70. And at the same time, P4 finishes its IO and comes back into the system, into the ready queue with a CPU burst, remaining CPU burst of 4. So initially it was 8, 4 units of processing is done. Now remaining unit of processing of P4 is 4. So P1 is getting executed. Since it finished its execution, it exits. Now the next process that will be given to the CPU for execution is P4 or P2. Now, if you see, P4 is having a smaller CPU burst, but the priority algorithm selects the job which is having a higher priority. The lower the number indicates the higher the priority. So here, P2 will be allocated to the CPU for execution, even though another process entered the system, but that process is having a lower priority than this process. So P2 is given for CPU for executed. So P2 is getting executed. When P2 leaves the system, then only the next priority will be provided the CPU. So the CPU is now allocated to P6 and it is getting executed. When it exits, that is when P4 gets the processing. So P4, though it had come into the system first and it was having the least processing CPU burst, but still it was the last to finish because it was having a lower priority. Now let's see the primitive version of this system. In the primitive version, again, P2 has entered the system. It has got execution, CPU for execution, and as it is executing, there is another process that comes in. Now this process is having a priority of 4 in red, if you see. So this is not disturbing the current process in execution because its priority is 2, which is higher than the P4's priority. But now P1 comes into the picture with a priority of 1. Now if you see, P2, which was of lower priority, gets out of the CPU and this process P1 will be allocated to the CPU for execution. So P1 is now getting executed in the CPU. It goes into an IO and hence from the ready queue, the next process which is of higher priority will be given to the CPU for execution. So again, P2 got a chance to execute and then P6 with a priority of 3 also enters the system. P2 finished its execution and it exited. Now in the ready queue, there is P3 and P4. So which process will be given priority? Yes, P3, P6, which is having a priority of 3. So that gets executed and then since P1 finished its IO processing, it comes back into the ready queue and it will be executed. It will print the running process and it will take the charge of the CPU for its execution. So that is priority scheduling. So priority scheduling, the problem with priority scheduling can be that it can make some process to starve. What do you mean by some processes to start? Now you just now saw that one process was having a priority of 1. So when it finished IO, it came back into this ready queue and it preempted the running process and it took over the system. Supposing in the system, if there is only higher priorities that are coming up, higher priority processes coming up into the ready queue, then the lower priority will never get a chance to execute its program. Hence, this situation is called starvation. That means that process with a lower priority will never get a CPU for execution. So that is why it is called as starving. So next algorithm is round robin algorithm. The round robin algorithm uses a time quantum. Time quantum means that whatever CPU time is there, it will be allocated equally to all the processes in the system. Now here we have 4 processes, P1, P2, P3, P4. All 4 processes will be given the CPU an equal amount of time for each of these CPUs, each of these processes will be given of the CPU. Like now P1, here time quantum is specified as 5 milliseconds. So you see the P1 is executed for 5 milliseconds and then the next process will be given the CPU. So P1 finishes 5 milliseconds. As soon as it finishes 5 milliseconds, it goes to the end of the ready queue and then P2 gets the CPU for execution. Next, P3 gets the CPU for execution. So in this way, every process is given a chance for 5 milliseconds. So within that 5 milliseconds, if the process finishes its execution and it leaves the CPU automatically, then that also is valid. Then the next process in the waiting queue, ready queue, will be allocated to the CPU. So in this way, a process in round robin, time quantum and context switch time has a relation. Now let's see this. If you see, the process times are here for the first queue. It is first example, that is process time is 10 milliseconds. So for that we have given a time quantum of 12 and the context switch is 0. That means that process is not removed from the CPU because it is time quantum is 12 milliseconds and the CPU burst is 10 milliseconds. It finishes before the time quantum finishes. But if you change the time quantum to 6, then the process has to be preempted once. So even though that is a single process running in the system, it will be removed from the CPU and again put back into the CPU for execution. So one context switch is required. If you give a time quantum of 1, then the number of context switches that will take place is 9. So it means that much amount of extra time will be used for processing because the current process has to be removed and again it has to be put back because it has to work only for time quantum. After time quantum, even if there is no process in the ready queue, it will context switch that process by itself. So that is the waste of time. So as you reduce the time quantum, if there are n processes also, if you have lesser time quantum, then there will be no number of context switches will be more. And if you have higher quantum, then the context switches will be low. So you need to make a proper balance between time quantum, because if you have higher time quantum also, then the process will be like the processing will be like first come first serve and it will have no effect of round robin. So you should have a proper balance between the quantum time and hence have a lesser number of context switches, but also take care that each process gets the CPU equally for execution. Round robin, also we have to see the turnaround time varies with the time quantum. So obviously when you have number of context switches are more, the turnaround time also will change. So here if you see, there is time quantum as 1, 2, 3, 4, 5, 6, and here we have on our y-axis we have the average turnaround time. So if the time quantum is 1, then the turnaround was 11. If the time quantum is 2, the turnaround is 11.5. If the time quantum is 3, then the turnaround time changed to somewhere less than 11. So like this, if you see, it goes on changing. If you For a time quantum 6 and 7, the turnaround was 10.5. So you need to take care that the time quantum that you choose should be very wisely chosen. Next is multi-level queues. Now we saw that there are different queues. We can use these queues. Multiple ready queues can be created with different types of scheduling algorithm assigned to them. Like for example, here we can have multiple queues, and for each of the queues we can give a priority from lowest priority to highest priority. That means any process that enters into the system processes, that means operating system processes should be given higher priority. Interactive processes that require user interactions more, should be given higher priority, and lesser than operating system processes. Next we have interactive editing processes. So this is a mid-level priority. Batch processes are having lower priority and student processes are having the least priority. So in this way, we can have different queues and ready queues, and each of these ready queues can be given priority. So processes, when they enter into this priority queues, based on that the CPU will be allocated. Again, here there is a drawback that if there are system processes continuously entering the system, then the other queues may not get the CPU for execution. So the best way is to use a multi-level feedback queue. In a multi-level feedback queue, a process will enter, for example, here we can have a round robin for the first queue, and we can have a time quantum of 8. Then if that process doesn't finish within that 8 milliseconds, then we can put it into the next queue, which is of a quantum of 16. Then again, if it doesn't finish within that, then it means that the process is too huge to finish, so we will put it into an FCFS queue. So in this way, each of these queues, the process will be pulled, but first a time quantum of 8, that means the smallest job will get executed first, and if it doesn't get executed, then we will put it into the next queue with a quantum of 16. There also, if it doesn't finish, then it will go in for a FCFS, first come first serve basis. Next we'll see thread scheduling. Now what are threads? Now you'll know that process is a system that is a program in execution, and this process gets memory and other resources allocated to it. A thread is a part of the process. That means in one process you can have multiple smaller processes. This multiple smaller processes are what are called as thread, and thread is defined as it's a lightweight process, whereas a process is called a heavyweight process, whereas a thread is a lightweight process, because a thread runs within the memory of a process. A thread is like a child of a process which runs within the memory of the process. So that's why it is called thread. It's a lightweight process. So thread scheduling means what? Thread scheduling means in a process you can have more than one thread running. Example is, I have already talked to you all about this example probably, that there is Windows Office document wherein we can type, as well as while we are typing we can also have the auto spell check, and we can have grammar check and formattation check. So this will be done automatically. So there are multiple threads that are simultaneously running while we are typing the text, and the document is reading this data that we are typing. So these threads, they are scheduled to the CPU. So each of these threads are allocated CPU. So thread scheduling and processor scheduling is not much different, but we will see this thread scheduling when we will see multi-threading section unit, because we need to understand the kernel thread and user threads for this, and this we will discuss in multi-threading section, which is following this lecture. Multiprocessor scheduling. What do you mean by multiprocessor scheduling? Now I told you about multi-programming. Multi-programming is more than one program is in ready queue and it is allocated to the CPU. Now till now, whatever example we have seen only one CPU. But here in this we can have multiple CPUs in the system. Now you all are aware of systems which are quad core and octa core and all that. What are those? That means there are 4 CPUs or 8 CPUs that are working together to give you more CPU or more execution, faster executions. So in this also there is scheduling happening. So the processes can be homogeneous processes or heterogeneous processes. Homogeneous processes means all are similar kind of applications that are running. Heterogeneous means a lot of different kinds of applications that are running. So in this case, the CPUs, the multiprocessor scheduling algorithms, have to take care of load balancing. That means that a single processor should not, or a single CPU should not be given all the processes to execute. All processes that are waiting in the ready queue should be allocated to each of these processes equally and uniformly. These processes can be running in a master-slave manner, wherein the master is controlling what the other processes have to execute. So in that case, the master is having all the data and slaves are only executing some part of the main process. So a single process is taking care of the work that has to be allocated to other processes. So in this case, load balancing is what is the important thing to do. So this multiprocessor system can be asymmetric multiprocessing or symmetric multiprocessing. You have already understood what is asymmetric multiprocessing and symmetric multiprocessing in first unit. So here we are only trying to understand that asymmetric multiprocessing is only one processor accesses the system data structure, elevating the need for data sharing. Whereas in symmetric multiprocessing, each processor is self-scheduling. So every process takes up a different process and executes it differently. So all the processes in the common ready queue are shared between all the CPUs. It means one processor picks one ready queue process and executes it. So each has its own private queue or ready queue. It can be having a common queue, or it can have, each of these processors can have their own ready queue. So this is what is multiprocessor scheduling. So in multiprocessor scheduling, processor affinity is what is the most another important thing that you need to remember. Processors have an affinity. If processors have an affinity means what? If supposing the process P1 is allocated to processor P1, processor 1. So when it goes for an IO and comes back for execution, it may want to go to processor 1 only, not to processor 2. So that is what is affinity, processor affinity. This processor affinity can be a soft affinity or a hard affinity. Soft affinity means it will wait to see if it can get processor 1. If it cannot get processor 1, then it goes to processor 2. Hard affinity means if a process has been processed by processor 1, then it will obviously try to go to CPU 1 only, not to CPU 2. It will wait for CPU 1 only to execute its process. Next lecture we will look at problems on CPU scheduling. Thank you.